In this video, we're going to use a simulation to help us understand a critical value. In particular, we're going to try to understand a critical value for confidence intervals generated using a standard normal distribution or a normal distribution. Okay, so we'll use a scenario of life expectancy. So I'm going to switch the statistic to mean since life expectancy is a population mean. All right, the distribution we're going to use is normal, and the method is z with sigma. All right, currently right now in the United States, the life expectancy is 75.5 years of age. The standard deviation is 5 years, and we're going to generate a bunch of confidence intervals of size 30, based on samples of size 30. So we'll generate about 1,000 of those. So generate 1,000 confidence intervals based on samples of size 30. And we're going to use a confidence level of 95%. All right, so there's our distribution. If we did this in the long run, meaning over and over again, we would expect 95% of these confidence intervals to capture the mean, meaning the vertical line would pass through the confidence intervals we generated, and about 5% of the confidence intervals, which are the ones in red, will not capture it. Okay, so in this simulation, about 95.4% of the confidence intervals capture the mean. All right, so what's a critical value? Well, a critical value helps us distinguish between good sample means and bad sample means. And what I mean by this, a sample mean is bad if it generates a red confidence interval, meaning it doesn't capture the true value. A good one is a green confidence interval that does capture the true value. So the critical value helps us decide what's between a good and bad sample mean. And this comes down to looking at the sampling distribution of sample means, which you see right here. So good sample means are going to be, the common sample means, and the bad sample means are going to occur in the tail of our sampling distribution. So we know by the central limit theorem that the sampling distribution of means is going to be normal. Okay, and so that's why you see this mound shape here. And bad sample means occur in the tail. And green sample means converge more on where the mean of the sampling means distributed. The mean of the sample means is, which currently is 75.5, right in the middle. So a critical value distinguishes between bad and good sample means, and so you can see that here where the red and green start separating. Okay, those are the critical values. We use the Z, or we use the standard normal when we do this using the theoretical approach, but this is a simulation of the sampling distribution. But you can see that it's happening in this particular case, since it's a confidence level of 95%, about 2 standard deviations above and below the sample mean. So of the population mean here of 75.5. So the standard deviation for the sampling distribution is about 0.9. And so if you go 0.9, 2 standard deviations above, so about 0.18 from 75.5, you would be right here. If you go down 2 standard deviations, about 1.9 or 0.9 down 2 standard deviations below, you'll occur right about here. You can calculate what that is by just taking your mean here and subtracting off 2 times this number, or adding 2 times that number to get whatever that would be here. But that's where the critical value is going to occur. So it's about 2 standard deviation. More realistically, about 1.96. So if you recall from the empirical rule, 95% of your observations to fall within 2 standard deviations of a mean if it's a normal curve. And so that's what a critical value just helps us decide between bad and good. So you can see that if we change our confidence level, because critical value depends on the confidence level, if I change it to 90, now we're allowing for more red confidence intervals. So what you will see here is that we'll see more red confidence intervals. And in our distribution, we're going to see that our tail is going to allow for more bad sample means. And so let's go ahead and recalculate, and you're going to see the tails have a little bit more red. And there you go, you see more red. Okay. And so if we go higher to 99, you're going to get less red because you're pushing the critical value out towards the tail more. Okay, so the divide where they start turning red and green, that's where the critical value occurs. Okay, so if I go to 99, you're going to see that we're going to get less red because we're pushing the critical value further out. We're going to get 99% of the area between those critical values to be green here. That's essentially what's going on. And you can see you pushed it out, so now you have about 95% of these sample means are good sample means, where about 0.01% or 1% are bad. And that's the intuition of a critical value.